Welcome to Science Snippets Fun Facts and Trivia. Today, we bring you Infinite Energy, How to Extract Power from Quantum Vacuum. Chapter 1. Introduction to Quantum Vacuum. Section 1. What is quantum vacuum? Welcome to a world where what we think of as nothing is actually brimming with energy and complexity. The concept of the quantum vacuum is one of the most fascinating and mind-bending ideas in modern physics. But what exactly is a quantum vacuum? And why has it captured the curiosity of scientists and inventors for decades? Unlike the classical idea of a vacuum, which is simply empty space devoid of matter, a quantum vacuum is far from being truly empty. It's a seething, dynamic field of particles and energy that constantly fluctuate, even in the most perfect vacuum imaginable. According to quantum field theory, space itself is made up of countless energy fields. And even when these fields are in their lowest energy states, they are never completely at rest. What this means is that the quantum vacuum is not just a void of emptiness, but a complex and active arena, where particles can spontaneously pop into existence and vanish in an instant. This phenomenon is known as quantum fluctuation. In essence, particles and antiparticles are constantly being created and annihilated, driven by what's called the Heisenberg uncertainty principle. This principle states that certain pairs of physical properties, like energy and time, cannot both be precisely known at the same time. As a result, brief violations of energy conservation are allowed, giving rise to these virtual particles. One of the most astonishing aspects of the quantum vacuum is its connection to the concept of zero-point energy. Even at a temperature of absolute zero, where all thermal motion theoretically stops, quantum fluctuations persist. This perpetual state of activity suggests the existence of a vast, untapped reservoir of energy spread throughout the universe. But how much energy are we talking about? Theoretical calculations suggest that the energy contained within just 1 cubic centimeter of vacuum could be astronomically high. Some estimates even propose that it could surpass the energy of all the nuclear power plants on Earth combined. However, there's a catch so far. No one has figured out how to extract this energy in a practical or efficient way. Yet, if such a source of energy could be harnessed, it would revolutionize our understanding of physics and provide humanity with a potentially limitless supply of clean energy. No pollution, no fuel consumption, just pure energy drawn from the very fabric of space itself. But as with most ideas that seem too good to be true, there are many challenges and controversies surrounding the notion of harvesting quantum vacuum energy. To truly grasp what makes this idea so compelling, we first need to explore the nature of zero-point energy itself. What exactly is it? And why has it captivated the imagination of scientists, futurists, and even conspiracy theorists? In the next section, we'll dive deeper into the mysterious world of zero-point energy and begin to unravel the secrets that may one day transform our world. Section 2. The mysterious zero-point energy. If the concept of the quantum vacuum is fascinating, then zero-point energy is the crown jewel of that fascination. So, what exactly is zero-point energy? And why does it generate such intense curiosity among scientists, futurists, and even conspiracy theorists? Zero-point energy refers to the lowest possible energy that a quantum mechanical system can have. Unlike classical systems where particles can be completely motionless at absolute zero temperature, quantum systems retain a certain amount of intrinsic energy even at this point. This is because particles, according to quantum mechanics, are never truly at rest. Instead, they are in a constant state of fluctuation due to the inherent uncertainties of the quantum world. This concept emerged from early 20th century quantum physics and was first theorized by prominent physicists like Max Planck and Albert Einstein. However, it was the work of Werner Heisenberg and Erwin Schrödinger that truly established the foundation for understanding zero-point energy. Heisenberg's uncertainty principle and Schrödinger's wave equation demonstrated that the energy of a system could never be precisely zero. Due to the probabilistic nature of particles at the quantum level, the implications of zero-point energy are nothing short of mind-blowing. It suggests that empty space, the so-called vacuum, is teeming with an unimaginable amount of energy. Some theoretical calculations have even suggested that the energy density of the quantum vacuum could be equivalent to 1 trillion times the energy output of the entire sun. If this energy could be harnessed, the potential applications would be beyond revolutionary. But why is this energy so elusive? The main problem is that zero-point energy is the ground state energy of a system. Extracting energy from it would require forcing the system into a state of even lower energy, something that, according to our current understanding of physics, should be impossible. However, some theorists propose that temporary fluctuations, or interactions with quantum fields, might allow for small amounts of energy to be extracted under the right conditions. One of the most intriguing pieces of evidence supporting the existence of zero-point energy is the Casimir Effect, a phenomenon predicted by Dutch physicist Hendrik Casimir in 1948. When two uncharged, parallel metal plates are placed extremely close to each other in a vacuum, they experience a tiny attractive force due to the suppression of certain wavelengths of quantum fluctuations between them. This experiment, which has been successfully demonstrated numerous times, provides tangible proof that the quantum vacuum is not an empty void, but a sea of fluctuating energy. Despite this, no practical method for extracting useful energy from the quantum vacuum has yet been developed, but the potential is too alluring to ignore, and researchers around the world continue to explore the possibilities. In the next section, we'll delve into how quantum field theory helps explain this bizarre phenomenon, and why it suggests that zero-point energy may be more than just a theoretical curiosity. Section 3. Why this topic fascinates scientists. Why does the concept of zero-point energy continue to captivate the imagination of scientists, engineers, and dreamers worldwide? The answer lies in the profound implications it holds for our understanding of the universe and the possibilities it presents for technological breakthroughs. First and foremost, zero-point energy challenges our traditional views of energy and matter. According to classical physics, energy must be derived from some form of matter or interaction, such as burning fuel or harnessing sunlight. But zero-point energy suggests that a staggering amount of energy exists within the very fabric of space itself, even when no matter appears to be present. If this energy could be harnessed, it would represent a new, inexhaustible power source, one that could potentially solve the global energy crisis and eliminate humanity's reliance on fossil fuels. From a theoretical standpoint, zero-point energy also plays a critical role in our understanding of quantum field theory and even cosmology. Many physicists believe that unlocking the secrets of zero-point energy could provide deeper insights into the unification of quantum mechanics and general relativity, two foundational theories of modern physics that remain stubbornly incompatible. Some even speculate that understanding Vacuum energy could hold the key to discovering a theory of everything. A complete framework that explains all fundamental forces and particles in the universe. Moreover, the potential technological applications of zero-point energy are nothing short of revolutionary. If a way could be found to tap into this energy, it could provide a source of power that is clean, limitless, and efficient. Imagine spacecraft propelled by quantum vacuum energy, enabling us to travel between planets, or even between stars, without the need for conventional fuel. Imagine cities powered indefinitely by a source of energy that never depletes. Furthermore, the sheer mystery of zero-point energy and its seemingly paradoxical nature fascinates scientists on a philosophical level. How can something come from nothing? How can a vacuum, which is supposed to be empty, be filled with energy? These questions force us to reconsider our most basic assumptions about reality and challenge our understanding of the universe itself. But it's not just mainstream scientists who are interested in zero-point energy. This concept has also attracted the attention of independent researchers, fringe theorists, and even conspiracy enthusiasts who claim that zero-point energy devices already exist, but are being suppressed by powerful interests. While most of these claims lack credible evidence, they highlight just how compelling the idea of limitless energy is. The search for a way to harness zero-point energy has inspired countless research papers, experimental designs, and speculative technologies. But while the dream remains elusive, many believe it's only a matter of time before we make a breakthrough. In the next chapter, we will dive deeper into the theoretical foundations that explain why zero-point energy exists in the first place. We will also explore the scientific principles that suggest this mysterious energy might be more than just a theoretical curiosity. Chapter 2: Theoretical Foundations. Section 1: Quantum Field Theory Basics. To truly understand zero-point energy and the quantum vacuum, we must first explore the fascinating world of quantum field theory (QFT). Unlike classical physics, which describes particles as distinct objects moving through space, QFT sees particles as excitations or disturbances within underlying fields that pervade all of space. In other words, particles are not fundamental entities. They are merely the visible manifestations of deeper, invisible fields. At its core, quantum field theory combines principles of quantum mechanics and special relativity to describe how these fields interact and fluctuate. According to QFT, every particle type, whether it's an electron, photon, or even a Higgs boson, corresponds to a unique quantum field. These fields extend throughout the entire universe, even in what appears to be empty space. Now, here's where things get truly fascinating. Even when a field is in its lowest possible energy state, known as the vacuum state, it is never completely at rest. Thanks to the Heisenberg uncertainty principle, fluctuations are inevitable. The principle states that you cannot simultaneously know a particle's exact position and momentum, or a field's precise energy level and time duration. This inherent uncertainty means that fields are constantly buzzing with virtual particles that momentarily appear and disappear. These vacuum fluctuations are the origin of what we call zero-point energy. Even when we remove all matter and cool the environment to absolute zero, energy remains within these fields. This means that what we perceive as empty space is actually a dynamic, restless environment where energy is continuously being exchanged. An important aspect of QFT is the way it describes particle interactions. When two particles interact, They do so by exchanging force-carrying particles, known as gauge bosons. For example, electromagnetic interactions occur through the exchange of photons, while gravitational interactions, in theory, would involve hypothetical particles called gravitons. These interactions are calculated through complex mathematical equations known as Feynman diagrams, which help scientists visualize and predict quantum events. The implications of quantum field theory are profound. If particles are merely excitations of underlying fields, then manipulating these fields might allow us to extract energy directly from the quantum vacuum. This idea has inspired countless theoretical papers, and even some experimental attempts to detect usable energy. However, doing so remains one of the greatest challenges in modern physics. Furthermore, QFT also suggests that the quantum vacuum may play a crucial role in explaining some of the deepest mysteries of the universe, including dark energy and the cosmological constant problem. The fact that quantum fluctuations are real, as demonstrated by experiments like the Casimir Effect, proves that the quantum vacuum is not a mere theoretical construct, but a measurable phenomenon with potential applications waiting to be unlocked. In the next section, we will delve into how these vacuum fluctuations give rise to measurable effects, and why they suggest that zero-point energy is more than just a bizarre curiosity. Could these mysterious fluctuations actually be harnessed to produce limitless energy? We'll begin to unravel that mystery next. Section 2. How vacuum energy emerges. Now that we've established the basics of quantum field theory, let's take a closer look at how vacuum energy actually emerges from the quantum world. The key to understanding this lies in the nature of quantum fluctuations. As we mentioned earlier, even in a vacuum state where no particles should exist, energy fields are never truly at rest. This restless state results from the Heisenberg uncertainty principle, which allows brief violations of energy conservation over incredibly short time scales. These temporary fluctuations cause particles and antiparticles to appear spontaneously before annihilating each other, releasing energy in the process. So, how does this translate into what we call vacuum energy? When quantum fields are in their lowest energy state, known as the ground state, they still retain a minimal amount of energy. This is the infamous zero-point energy. Theoretically, this energy is present everywhere in the universe, meaning that even the emptiest regions of space contain a staggering amount of untapped energy. One of the most compelling pieces of evidence for vacuum energy is the Casimir Effect, an experimental phenomenon first predicted by Dutch physicist Hendrik Casimir in 1948. When two metal plates are placed extremely close to each other in a vacuum, they experience a tiny but measurable force pulling them together. This effect occurs because the plates restrict certain wavelengths of quantum fluctuations between them, creating a pressure imbalance caused by the surrounding vacuum energy. But the Casimir effect is not the only evidence supporting the reality of vacuum energy. The concept also plays a crucial role in explaining other quantum phenomena, such as Lamb shifts, tiny shifts in the energy levels of atoms caused by interactions with vacuum fluctuations. The real question, however, is whether this energy can be harnessed in a practical way. Despite the overwhelming evidence that vacuum energy exists, extracting it for useful purposes remains one of the most daunting challenges in physics. The problem lies in the fact that zero-point energy is a ground state energy. To tap into it, we would need to lower that energy even further, something current scientific theories suggest is impossible. Yet, The sheer magnitude of the energy present in the quantum vacuum continues to inspire researchers to search for loopholes. Could there be a way to temporarily access or manipulate this energy without violating the fundamental laws of physics? In the next section, we will explore the Casimir effect in more detail and discuss how it has become one of the strongest pieces of evidence supporting the existence of vacuum energy. We'll also see why this phenomenon might offer hints about how to unlock this mysterious power source. Section 3. The Casimir Effect Proof of Vacuum Energy. Among the various phenomena that hint at the existence of vacuum energy, the Casimir effect stands out as one of the most compelling pieces of experimental evidence, discovered by Dutch physicist Hendrik Casimir in 1948. This fascinating effect demonstrates that even in a perfect vacuum, energy fluctuations are still at play. So, what exactly is the Casimir effect? Imagine two uncharged, parallel metal plates placed extremely close to each other, just a few nanometers apart, in a vacuum. According to classical physics, nothing should happen, because there's no matter or electromagnetic force acting between them. However, quantum mechanics tells a different story. In the quantum vacuum, virtual particles are constantly popping in and out of existence due to quantum fluctuations. These fluctuations create electromagnetic waves of all possible wavelengths. However, when two plates are positioned very close together, only certain wavelengths can fit between them. This restriction means that the density of quantum fluctuations between the plates is lower than the density outside them. The result? A measurable force pushing the plates toward each other. This force is incredibly tiny, but it has been measured and confirmed through numerous experiments. Its existence provides solid proof that the quantum vacuum is not empty, but instead filled with fluctuating energy. But the implications go even further. The Casimir effect suggests that vacuum energy is not just a theoretical curiosity, but a real, measurable phenomenon. More intriguingly, it hints that this energy can, in some cases, exert forces and produce physical effects. Some researchers believe that by better understanding the Casimir effect, we might uncover practical ways to harness vacuum energy. For example, manipulating the separation between specially designed surfaces could potentially create mechanisms that convert vacuum energy into usable power. However, this remains purely speculative, and no practical technology has yet been developed. The importance of the Casimir effect cannot be overstated. It's a rare glimpse into the hidden energy of the universe, demonstrating that empty space is far more complex than it appears. Moreover, it provides a foundation for further research into how vacuum energy could be manipulated or harnessed. In the next chapter, we'll dive into the various attempts scientists have made to tap into this mysterious energy source. From early speculative experiments to cutting-edge theories, we'll explore why extracting zero-point energy has proven to be so difficult, and whether there's hope for success in the future. Chapter 3. Attempts to harness vacuum energy. Section 1. Early experiments and failures. The idea of harnessing vacuum energy has fascinated scientists and inventors for decades. After all, if the quantum vacuum is truly filled with limitless energy, then finding a way to tap into it would be a monumental achievement. Unfortunately, the path to unlocking this mysterious power source has been littered with failed experiments and unproven theories. One of the earliest attempts to extract energy from the quantum vacuum came during the mid-20th century, shortly after the Casimir effect was first demonstrated. Visionary inventors and fringe researchers alike became captivated by the possibility of converting zero-point energy into usable power. However, their efforts were largely based on speculation, rather than solid scientific principles. Many of these early experiments focused on creating devices that claimed to interact with the zero-point field. Some inventors designed elaborate electromagnetic systems, hoping that high-frequency oscillations could somehow draw energy from the vacuum. Others attempted to build mechanical devices that could allegedly tap into the energy fluctuations permeating space. However, these machines consistently failed to produce any measurable results, leading mainstream scientists to dismiss such efforts as pseudoscience. One infamous example is the so-called free energy devices that circulated throughout the late 20th century. Promoters of these machines claimed to have discovered methods for extracting zero-point energy, often with dramatic promises of solving the world's energy problems. However, when put to the test, these devices almost always failed to deliver reproducible results. Worse still, many of these claims were later exposed as scams or overhyped misunderstandings of quantum physics. Despite these failures, the concept of zero-point energy continued to attract serious scientific interest. Researchers began to realize that while the theoretical potential of vacuum energy was enormous, the practical challenges of accessing it were equally daunting. The fundamental problem lies in the nature of zero-point energy itself. It is the lowest energy state of a quantum field. Therefore, to extract energy from it, one would have to somehow push the field to a state of even lower energy, something that our current understanding of physics deems impossible. Nevertheless, some legitimate research efforts were made to investigate whether the Casimir effect or other quantum phenomena could be exploited to harness vacuum energy. However, all attempts thus far have been unsuccessful in producing a net positive energy output, even though certain experiments demonstrated that quantum fluctuations could create measurable forces. No one has yet found a way to convert this effect into a reliable energy source. The failures of these early attempts have not discouraged researchers from continuing to explore the possibilities. Instead, they have motivated scientists to develop more sophisticated theories and experimental techniques. Today, while most of the work remains theoretical, the dream of harnessing zero-point energy persists. In the next section, we will look at modern theories and hypotheses that aim to overcome the challenges faced by early researchers. Could the key to unlocking zero-point energy lie in a deeper understanding of quantum field interactions? Let's find out. Section 2. Modern theories and hypotheses. Despite the failures of early experiments, modern scientists are far from giving up on the quest to harness zero-point energy. Instead, they have refined their theories and developed more sophisticated approaches aimed at unlocking the mysterious energy embedded in the quantum vacuum. One of the most promising ideas revolves around manipulating quantum field interactions. According to certain hypotheses, altering the vacuum state itself might allow for energy extraction without violating the fundamental principles of physics. A notable approach involves the dynamic Casimir effect, which differs from the standard Casimir effect by involving rapidly moving mirrors or surfaces. By accelerating boundaries at high speeds, virtual particles could be transformed into real particles, potentially producing measurable energy. Additionally, advancements in quantum electrodynamics (QED) and quantum chromodynamics (QCD) have inspired new ways of thinking about vacuum energy. Some researchers speculate that interactions between quantum fields could be manipulated, to release energy under special conditions. Theories involving vacuum polarization, the process by which a vacuum behaves like a medium with fluctuating charges, have gained particular attention as a potential pathway to extracting energy. Another area of interest involves creating and utilizing metamaterials, artificially engineered materials with properties not found in nature. By designing materials that interact uniquely with electromagnetic fields, scientists hope to manipulate vacuum energy in ways previously thought impossible. This idea remains theoretical, but offers intriguing possibilities for future experimentation. Additionally, concepts related to negative energy, states and exotic matter have been proposed as potential mechanisms for accessing vacuum energy. Some physicists believe that if negative energy could be produced or manipulated, it might create conditions where energy extraction becomes feasible. However, such ideas remain highly speculative and are met with skepticism by the mainstream scientific community. Theoretical physicists are also exploring connections between zero-point energy and phenomena like dark energy and the cosmological constant problem. If vacuum energy truly exists at the levels predicted by quantum theory, it could hold the key to solving some of the biggest mysteries of the universe. While most of these theories are still in the conceptual phase, they represent a significant evolution from the speculative ideas of the past. Modern researchers are developing advanced mathematical models and experimental techniques aimed at proving or disproving these hypotheses. In the next section, we will examine the technological challenges that continue to hinder progress. Despite the fascinating theories, practical implementation remains elusive. What obstacles must be overcome to make zero-point energy a reality? Let's find out. Section 3. Technological Challenges and Breakthroughs. Even with promising theories about zero-point energy, turning those ideas into reality presents a series of daunting technological challenges. Extracting energy from the quantum vacuum is not just a matter of building a sophisticated machine. It requires fundamentally rethinking how we interact with the underlying structure of space itself. The first major challenge is that zero-point energy represents the lowest possible energy state of a quantum field. To tap into it, one would have to find a way to reduce the energy state even further, or somehow manipulate the fluctuations in a controlled manner. This idea appears impossible, based on our current understanding of quantum mechanics. But researchers are still searching for loopholes or alternative approaches. One area of investigation involves enhancing the dynamic Casimir effect, which attempts to transform virtual particles into real ones by rapidly accelerating mirrors or surfaces. While some experimental setups have demonstrated the ability to produce radiation through this method, the energy output remains minuscule. Scaling this process to a practical level is a challenge that has yet to be overcome. Another technological obstacle lies in the creation of metamaterials capable of interacting with vacuum energy fields. Designing materials with precise electromagnetic properties that can manipulate quantum fluctuations is a complex task. While some theoretical models suggest it's possible, the practical engineering required is still far beyond our current capabilities. Furthermore, the potential use of negative energy states and exotic matter presents its own difficulties. Even if such states can be created, maintaining and controlling them without causing instability remains a massive technological hurdle. Beyond the technical challenges, there is also the issue of detectability and measurement. If vacuum energy can be harnessed, there needs to be a reliable way to measure and control the extracted energy. Current experiments have only been able to demonstrate vacuum effects indirectly, like the Casimir effect. but never on a scale that would be useful for practical energy production. Despite these obstacles, there are reasons to be hopeful. New experimental techniques in quantum optics, nanotechnology, and high-energy physics continue to push the boundaries of what is possible. Some researchers are even considering hybrid approaches, combining aspects of multiple theories to enhance their chances of success. Breakthroughs may not come soon, but as our understanding of quantum fields and advanced materials continues to evolve, the possibility of unlocking zero-point energy becomes more realistic. The next chapter will explore the potential applications of vacuum energy and how it could revolutionize everything from power generation to space travel. But first, we need to understand what makes this energy source so appealing and how it could change our world forever. Chapter 4: Potential Applications. Section 1: Unlimited Clean Energy. If zero-point energy could be harnessed, the most obvious and enticing application would be as a source of unlimited clean energy. Imagine a world where energy is extracted directly from the fabric of space itself, providing power that is not only abundant, but also completely free of harmful emissions or environmental impact. The appeal of such a power source is undeniable. Unlike fossil fuels, which contribute to pollution and climate change, zero-point energy would produce no greenhouse gases or toxic byproducts. It wouldn't require massive infrastructure for mining, drilling, or transportation, and it would be available anywhere on Earth or even in deep space. The sheer potential of zero-point energy is staggering. Some estimates suggest that the amount of energy contained within a single cubic centimeter of vacuum could theoretically exceed all the energy produced by humanity's power plants combined. If even a tiny fraction of this energy could be converted into usable power, it would be more than enough to meet the world's energy demands indefinitely. Furthermore, a reliable source of zero-point energy could make current renewable energy technologies like solar, wind, and geothermal power obsolete. While these methods have their advantages, they also have limitations, such as dependency on weather conditions or geographic constraints. Zero-point energy, on the other hand, would be constant and available everywhere, regardless of time or location. Additionally, the cost of energy production could be reduced to near zero levels. Once a functioning device or system capable of extracting vacuum energy is developed, the operational costs would be minimal. This could dramatically lower the cost of living, improve the quality of life worldwide, and even play a major role in alleviating poverty by providing cheap and reliable energy access to developing nations. But it's not just about cheap electricity. If zero-point energy could be harnessed effectively, it would open the door to technological advancements currently limited by our energy resources. Supercomputers, artificial intelligence systems, and even high-energy experiments could operate without concerns about power consumption. Moreover, entire cities could be powered by devices small enough to fit in a single building. Of course, all of this remains hypothetical, despite the compelling theories and tantalizing possibilities. No practical method of extracting zero-point energy has been demonstrated. However, the pursuit of this clean and limitless energy source continues to inspire researchers worldwide. In the next section, we will explore another exciting possibility: how vacuum energy could revolutionize space travel and propulsion, making interstellar exploration a practical reality. Section 2: Space Travel and Propulsion. If the idea of unlimited clean energy from the quantum vacuum sounds revolutionary, then its potential application in space travel is nothing short of extraordinary. The ability to harness zero-point energy could completely transform how we explore the cosmos, enabling technologies that are currently confined to the realm of science fiction. One of the biggest challenges in space exploration is propulsion. Traditional rocket engines rely on chemical reactions that produce high-speed exhaust gases to generate thrust. However, these systems are inefficient, expensive, and severely limited by the amount of fuel they can carry. Even the most advanced ion propulsion systems, while more efficient, are still constrained by their need for onboard fuel. Zero-point energy, however, could change everything. If we could tap into the vast energy present in the quantum vacuum, it could provide a constant and virtually unlimited power source for propulsion systems. Such systems would not rely on carrying massive amounts of fuel, but instead draw energy directly from the space around them. One theoretical concept that has captured the imagination of researchers is the idea of a warp drive, inspired by Einstein's theory of general relativity. A warp drive would manipulate space-time itself, creating a bubble that contracts space in front of a spacecraft and expands it behind. If zero-point energy could provide the immense power required to manipulate space-time, faster than light travel might actually become a reality. Another possibility involves using zero-point energy to power advanced anti-gravity or inertia-canceling devices. These technologies could revolutionize not only space travel, but also aviation and transportation on Earth. If gravitational or inertial forces could be controlled or negated, vehicles could move with unprecedented speed and efficiency. Furthermore, the ability to draw energy from the quantum vacuum could solve one of the most critical issues in space exploration, providing consistent power to spacecraft on long-duration missions. Current technologies like solar panels and nuclear batteries are effective, but have limitations. A spacecraft powered by zero-point energy could potentially operate indefinitely, opening the door to deep space exploration far beyond our solar system. However, these concepts remain purely theoretical, while researchers are developing mathematical models to explore how zero-point energy might be used for propulsion. Practical demonstrations are still far from being realized, but if even a fraction of the theories prove correct, the implications for space travel would be nothing less than revolutionary. In the next section, we will examine how harnessing zero-point energy could impact various technological innovations beyond power generation and space travel, potentially changing the world as we know it. Section 3. Revolutionary technological innovations. The potential of zero-point energy goes far beyond providing clean energy or revolutionizing space travel. If this mysterious power source can be harnessed, it could pave the way for groundbreaking technological innovations across numerous fields. One of the most exciting possibilities lies in the field of advanced computing. The immense energy present in the quantum vacuum could power supercomputers of unparalleled performance. Quantum computers, which already rely on quantum principles to process information, could reach levels of efficiency and processing power currently unimaginable. Complex simulations, artificial intelligence, and big data processing could be performed with near-infinite energy availability, accelerating technological progress by orders of magnitude. Medical technology could also experience a dramatic transformation. Devices powered by zero-point energy could lead to the development of portable, ultra-efficient medical equipment, enabling advanced diagnostic tools and life support systems to be deployed anywhere in the world. Medical research facilities could perform experiments previously deemed impossible due to energy limitations, pushing the boundaries of biotechnology and genetic engineering. Furthermore, the implications for telecommunications and information transfer are profound. If zero-point energy could be harnessed to manipulate quantum fields, it might be possible to develop new forms of communication that are instantaneous, reliable, and virtually limitless in capacity. Concepts like quantum entanglement and quantum teleportation, once considered pure science fiction, might become achievable with sufficient energy resources. Zero-point energy could also revolutionize transportation and manufacturing. For instance, if anti-gravity or inertia control technologies were developed, it could lead to the creation of frictionless transportation systems, making traditional vehicles obsolete. Factories powered by quantum energy could operate continuously, drastically reducing manufacturing costs and environmental impact. Additionally, military and defense applications would be inevitable. If nations gained the ability to harness zero-point energy, it could trigger an unprecedented technological arms race. Advanced energy weapons, defense shields, and propulsion systems would become real possibilities, fundamentally altering global power dynamics. However, beyond technological advancements, the potential societal impacts of zero-point energy could be even more significant. Energy scarcity has been a fundamental challenge throughout human history. Solving that problem could lead to a new era of prosperity and equality, where clean, unlimited power is available to everyone on the planet. But, of course, these possibilities remain theoretical. While the potential is staggering, the path to making zero-point energy a practical reality is fraught with challenges. In the next chapter, we'll address some of the ethical concerns and societal implications associated with unlocking such a powerful resource. Could humanity handle the responsibility of wielding limitless energy? And what would it mean for our world if we succeeded? Chapter 5: Ethical and Social Concerns. Section 1: Scientific Skepticism and Debates. Despite the incredible potential of zero-point energy, the concept remains surrounded by skepticism and intense debate within the scientific community. While many researchers acknowledge the theoretical existence of vacuum energy, most remain doubtful about the possibility of harnessing it for practical use. One major point of contention is the fact that zero-point energy represents the lowest energy state of a quantum field. According to established quantum mechanics, extracting energy from this ground state would require pushing the field to a lower state, something deemed impossible by current physics. Critics argue that even if fluctuations can be detected, as demonstrated by the Casimir Effect, this does not necessarily imply that the energy can be harvested in any meaningful way. Moreover, some scientists believe that claims of extracting zero-point energy often misinterpret or exaggerate quantum principles. Theoretical models predicting massive amounts of available energy often conflict with experimental data. In most cases, proposed mechanisms for energy extraction are purely speculative and lack empirical support. The history of zero-point energy research is also tainted by pseudoscience and fraudulent claims. Numerous inventors have presented so-called free energy devices that supposedly tap into the vacuum's energy. However, these devices consistently fail to demonstrate reproducible results under rigorous testing. This legacy of deception has only deepened skepticism and made serious researchers wary of pursuing what many consider to be a futile effort. Nevertheless, not all criticism is dismissive. Some physicists suggest that while practical extraction methods may be impossible, with our current understanding, further research could reveal loopholes or entirely new principles. theories involving dynamic Casimir effects, negative energy states, and metamaterials continue to be investigated, albeit cautiously. Another aspect fueling the debate is the concern over how powerful interests might influence or suppress research related to zero-point energy. Some conspiracy theories claim that breakthroughs in vacuum energy technology have already been made, but are kept hidden by governments or corporations to protect existing energy industries. While most of these claims lack credible evidence, they highlight the fear of technological suppression and the desire for a breakthrough that could benefit all of humanity. The controversy surrounding zero-point energy is not just about the science itself, but also about the implications of success. If vacuum energy could be harnessed, it would challenge many fundamental assumptions about physics and could disrupt the world's economic and political landscape. As researchers continue to explore the potential of this mysterious energy source, they must also navigate a minefield of skepticism, ethical concerns, and scientific rigor. In the next section, we will delve into the ethical implications of developing a virtually limitless energy source. How should humanity handle such power, and who gets to control it? Section 2. Ethical implications of unlimited power. The prospect of harnessing zero-point energy presents not only scientific and technological challenges, but also profound ethical dilemmas. If humanity ever succeeds in extracting this virtually limitless energy source, the consequences could be both revolutionary and catastrophic. The ethical implications of such power are impossible to ignore. First and foremost, there is the issue of control and accessibility. Who would have the authority to regulate and distribute zero-point energy? If it became a reality, would this revolutionary power source be controlled by governments, private corporations, or international organizations? The possibility of monopolization is a genuine concern. If only a select few entities gain control over this technology, it could deepen existing social and economic inequalities rather than eliminate them. Another critical issue is the potential for weaponization. Throughout history, humanity has demonstrated a tendency to turn powerful technologies into instruments of destruction. If zero-point energy can be harnessed, it could theoretically be used to create weapons of unimaginable power. Devices capable of manipulating quantum fields could have devastating effects on a global scale, far surpassing the destructive potential of nuclear weapons. Ensuring that such power is used responsibly would be one of the greatest ethical challenges ever faced. There's also the question of environmental impact. While zero-point energy is often presented as a clean, unlimited power source, it's still unclear what unintended consequences might arise from manipulating the quantum vacuum. Could extracting energy from this fundamental level of reality disturb the fabric of space itself? Would widespread use of this energy source have unknown and potentially irreversible effects on the universe? These questions remain unanswered. Additionally, the possibility of zero-point energy raises concerns about technological suppression and control. If powerful organizations or governments were to successfully harness this energy, would they choose to share it with the world, or keep it hidden for their own benefit? Some conspiracy theories already suggest that advancements in vacuum energy technology have been suppressed to protect the interests of the existing energy industry. While these claims are largely unproven, they underscore the public's fear of technological control and exploitation. Moreover, the ethical implications of zero-point energy are not only practical but philosophical. If we gain the ability to draw limitless energy from the universe, what responsibilities come with such power? Should humanity be trusted to wield it wisely? And how would it change our relationship with the natural world? Addressing these ethical concerns requires careful consideration, open dialogue, and international cooperation. The potential benefits of zero-point energy are staggering, but without ethical guidelines, they could lead to unforeseen consequences that might outweigh the advantages. In the next section, we will explore the possible social impacts of this technology, examining how it could reshape economies, cultures, and even our understanding of what it means to be human. Section 3. Potential social impact. The successful harnessing of zero-point energy wouldn't just be a scientific breakthrough. It would be a societal revolution. If humanity gains access to a virtually limitless energy source, the implications for our social structures, economies, and cultures would be profound and far-reaching. From an economic perspective, cheap and abundant energy could eliminate the world's dependence on fossil fuels, fundamentally reshaping global markets. Energy scarcity has long driven international conflict and economic disparity. If zero-point energy became accessible to everyone, it could level the playing field for developing nations, allowing them to rapidly industrialize without relying on outdated and environmentally harmful technologies. Moreover, unlimited energy could drastically reduce the costs of manufacturing, transportation, and everyday living. Industries heavily reliant on energy, such as agriculture, construction, and technology, could see unprecedented growth, boosting productivity, reducing poverty, and improving living standards worldwide. However, such a drastic shift would not come without challenges. Industries built around conventional energy sources could face collapse, leading to job losses and economic instability. Oil, coal, natural gas, and even renewables like solar and wind could all become obsolete almost overnight. Managing this transition would require careful planning and global cooperation to prevent economic disaster. Socially, the impact of zero-point energy could be equally transformative. As energy becomes universally accessible, remote areas of the world could experience a technological renaissance. Access to clean, cheap energy would enable better education, healthcare, and communication networks, potentially bridging the gap between developed and developing countries. Culturally, the availability of infinite energy could alter how humanity views its relationship with the natural world. With energy no longer being a limited resource, societies might shift away from exploitative practices toward more creative and sustainable endeavors. But there is also the danger of complacency, taking abundance for granted and failing to use it responsibly. The political landscape could also be reshaped dramatically. Nations with economies built on energy exports could lose geopolitical power, while those that develop zero-point energy technology might gain disproportionate influence. Such changes could lead to both international cooperation and conflict, depending on how fairly the technology is shared. Another concern is whether zero-point energy would truly be accessible to all. History shows that powerful entities often monopolize new technologies. Ensuring fair distribution would require not only technological breakthroughs, but also ethical governance and societal willpower. In short, zero-point energy could be the key to a brighter future, or a tool of unimaginable control. Its potential to reshape human society is both exciting and terrifying. In the next chapter, we'll explore the future of zero-point energy research. What are scientists doing today to unlock its potential? And could we be closer to a breakthrough than we think? Chapter 6: The Future of Vacuum Energy Research. Section 1: Current Research Efforts. Despite the challenges and skepticism surrounding zero-point energy, scientific interest in this mysterious power source has only grown. While most mainstream researchers focus on understanding the fundamental nature of quantum fields, a smaller but dedicated group is actively exploring how to harness vacuum energy for practical use. One of the most promising areas of research involves the dynamic Casimir effect. Unlike the standard Casimir effect, which requires fixed plates to generate force, the dynamic Casimir effect occurs when mirrors or surfaces are rapidly accelerated. This rapid motion can, in theory, convert virtual particles into real photons, producing measurable energy. Experimental setups using superconducting circuits have successfully demonstrated this effect on a small scale. Although the energy output remains minimal, another line of research focuses on developing metamaterials, artificially engineered substances with properties not found in nature. By carefully designing materials that interact with electromagnetic fields, scientists hope to create systems capable of manipulating quantum fluctuations in novel ways. While practical applications remain distant, early studies suggest that metamaterials could potentially enhance or modify vacuum energy interactions. Meanwhile, researchers working in the field of quantum optics are investigating ways to extract usable energy from vacuum fluctuations. Techniques involving high-frequency lasers and electromagnetic fields are being explored as potential methods to disturb the vacuum state and release small amounts of energy. While these experiments are still largely theoretical, they offer intriguing possibilities for future development. Additionally, advancements in quantum computing and particle physics are indirectly contributing to our understanding of zero-point energy. As scientists continue to refine their knowledge of quantum fields and vacuum states, the possibility of discovering practical methods of energy extraction remains on the table. Some even speculate that breakthroughs in quantum gravity or unified field theories could hold the key to unlocking vacuum energy. Funding for these projects remains limited, largely due to the speculative nature of the research. However, interest is growing, particularly among private institutions and independent researchers, who see the potential of zero-point energy as a revolutionary power source. Collaborative efforts between universities, government agencies, and private companies are slowly beginning to emerge. Despite the many obstacles, researchers are gradually making progress. Experiments are becoming more refined, theoretical models are being improved, and technological advancements continue to open new possibilities. While there is still a long way to go, the determination to unlock zero-point energy has never been stronger. In the next section, we will discuss the steps that need to be taken to turn these promising theories into practical technologies. What breakthroughs are still required, and how close are we to making zero-point energy a reality? Section 2. Steps needed for future breakthroughs. While current research efforts have made significant progress in understanding vacuum energy, the path to practical application remains a challenging one. Turning theoretical concepts into usable technologies will require a combination of scientific breakthroughs, technological innovation, and international collaboration. The first step is to improve our understanding of quantum field interactions. While the principles of zero-point energy are rooted in quantum mechanics, many aspects of how vacuum energy behaves remain unexplored. Developing more accurate mathematical models that describe the fluctuations of quantum fields will be essential for identifying realistic methods of energy extraction. Researchers must also investigate how these fluctuations can be manipulated or enhanced to produce usable energy. Secondly, experimental verification is crucial. Theoretical models are only as valuable as the experiments that confirm them. Current attempts to harness the dynamic Casimir effect and manipulate metamaterials need to be scaled up and refined. Improved experimental setups that can produce measurable and reproducible results will be necessary to prove that energy extraction from the quantum vacuum is truly feasible. Another important step involves the development of advanced materials and technologies. Creating devices capable of interacting with quantum fields at a meaningful scale requires precision engineering. Metamaterials designed to amplify vacuum fluctuations or systems capable of generating controlled negative energy states could provide the breakthroughs needed to move beyond theory. Collaborations between physicists, materials scientists, and engineers will be essential in making progress. Additionally, funding and collaboration must be prioritized. Research into zero-point energy has often been dismissed as speculative, resulting in limited financial support. To overcome this, governments, private institutions, and international organizations need to recognize the potential of vacuum energy research and provide resources to accelerate development. Funding interdisciplinary research projects and encouraging collaboration between institutions worldwide could drastically improve progress. Furthermore, scientists must address the ethical and societal implications of successfully harnessing zero-point energy, establishing guidelines for responsible use, and ensuring that the technology is accessible to all, rather than monopolized by powerful entities, will be critical. Finally, researchers must remain open to revising established theories. If current approaches continue to fall short, it may be necessary to reconsider fundamental assumptions about quantum mechanics and vacuum energy. Breakthroughs often come from challenging conventional wisdom, and the pursuit of zero-point energy will likely require bold new ideas. In the next section, we will look at the potential breakthroughs that could be on the horizon. Are we closer to achieving practical zero-point energy than we realize? And if so, what would that mean for our world? Section 3. Vision for the future. What if zero-point energy could truly be harnessed? The implications for humanity and our technological advancement would be nothing short of revolutionary. As researchers continue to push the boundaries of quantum physics, many believe that practical zero-point energy could become a reality within the next few decades. Imagine a world where energy is no longer a limited resource. Cities powered by devices drawing energy directly from the quantum vacuum could operate indefinitely without polluting the environment. Deserts could be transformed into fertile landscapes, and isolated communities could enjoy the same technological benefits as major urban centers. The global energy crisis would be over, paving the way for a new era of prosperity and environmental recovery. In the realm of space exploration, zero-point energy could make interstellar travel achievable. Spacecraft powered by vacuum energy would no longer be constrained by fuel limitations. Missions that currently take years could be completed in weeks or even days. Colonizing distant planets and exploring deep space would become realistic goals. Expanding humanity's reach far beyond our solar system. Technological advancements driven by zero-point energy could also revolutionize countless other fields. Quantum computing, artificial intelligence, medical research, and communication systems could all benefit from virtually limitless power. Devices previously confined to the realm of science fiction, like anti-gravity propulsion systems or energy shields, might finally become possible. However, Achieving this vision will require overcoming significant obstacles. As we've discussed, technological challenges, scientific skepticism, and ethical concerns must all be addressed. Before zero-point energy can become a practical reality, scientists will need to continue refining their theories, developing advanced materials, and designing experimental systems capable of proving that energy can be extracted from the quantum vacuum. Collaboration between governments, private institutions, and independent researchers will be essential. No single group or nation will be able to unlock the secrets of zero-point energy alone. Instead, international cooperation will be necessary to ensure that the technology is developed responsibly and shared equitably. Moreover, preparing for the societal impact of zero-point energy will be just as important as solving the scientific and technological challenges. Ethical guidelines, transparent policies, and public engagement will be crucial to ensure that this technology benefits all of humanity, rather than becoming a tool of oppression or exploitation. The journey to harness zero-point energy may still be in its early stages, but the progress made so far offers hope. With continued research, innovation, and global cooperation, the dream of unlimited energy could one day become a reality, and if it does, it could transform our civilization in ways we can scarcely imagine. In the final chapter, we will summarize what we've learned and consider how the pursuit of zero-point energy might shape the future of science, technology, and society itself. Chapter 7. Conclusion. Section 1. Summarizing the potential of quantum vacuum energy. The concept of zero-point energy remains one of the most fascinating and controversial topics in modern physics. From its theoretical foundations rooted in quantum field theory to the promising but elusive potential of harnessing vacuum energy, the journey to understand this phenomenon has been both inspiring and challenging. We have explored how zero-point energy emerges from the seemingly empty fabric of space, driven by quantum fluctuations that constantly occur even in the absence of matter. Unlike classical vacuums, which are assumed to be completely devoid of energy, the quantum vacuum is a dynamic and restless entity. Particles and antiparticles continually appear and vanish due to the Heisenberg uncertainty principle, producing a measurable effect known as the Casimir Effect. This phenomenon has provided undeniable proof that the vacuum is not empty, but instead teeming with energy waiting to be understood. The implications of harnessing zero-point energy are staggering. If this hidden power source could be extracted, it would provide humanity with a virtually limitless supply of clean energy. Pollution, fuel shortages, and energy crises could become problems of the past. Industries could flourish, transportation could be revolutionized, and even deep space exploration could become a practical reality. Zero-point energy has the potential to transform every aspect of human civilization, offering new solutions to some of the most pressing challenges facing our world. Moreover, the technological possibilities are just as exciting. Devices powered by zero-point energy could lead to groundbreaking advancements in fields like quantum computing, medical technology, telecommunications, and even anti-gravity propulsion. Concepts once relegated to science fiction might become achievable, pushing the boundaries of what humanity is capable of creating. However, despite the incredible potential, the path to practical zero-point energy remains full of challenges. Theories remain unproven, and experiments have so far only demonstrated small-scale effects. The technology needed to manipulate quantum fields and harness vacuum energy is still far from being developed. Additionally, scientific skepticism and ethical concerns must be addressed to ensure that this powerful energy source, if ever harnessed, is used responsibly and for the benefit of all. But while the obstacles are significant, so too is the determination of researchers worldwide. With advancements in quantum field theory, metamaterials, and experimental techniques, the possibility of unlocking zero-point energy is steadily moving from the realm of speculation to that of genuine scientific inquiry. The future remains uncertain, but one thing is clear: the quest to understand and utilize zero-point energy is far from over. The pursuit of this mysterious power source continues to inspire and challenge the brightest minds of our generation. In the next section, we will look at the specific challenges that must be overcome and the promising directions that may one day turn this incredible vision into reality. Section 2: Challenges and Promising Directions. As we've seen throughout this exploration of zero-point energy, the potential benefits are extraordinary, but the challenges are equally daunting. If humanity is ever to harness this elusive power source, several significant obstacles must be overcome. One of the most fundamental challenges lies in our limited understanding of quantum fields and vacuum energy itself. While theories like quantum field theory provide a framework for understanding how vacuum energy emerges, much remains unknown. The complex interactions between quantum fluctuations and electromagnetic fields are difficult to study, and developing accurate models requires advancements in both theoretical physics and experimental techniques. Additionally, the problem of energy extraction remains unsolved. Zero-point energy represents the lowest possible energy state of a quantum field, which makes it incredibly difficult to tap into. Even with promising concepts like the dynamic Casimir Effect and specially designed metamaterials, no practical method of extracting usable energy has been demonstrated. Researchers will need to find innovative ways to manipulate quantum fields without violating fundamental physical laws. Technological challenges also play a critical role. The creation of devices capable of manipulating vacuum energy requires extremely precise engineering and materials science. Advanced metamaterials, superconducting circuits, and high-frequency electromagnetic systems are just some of the tools that may be necessary to make progress. Developing such technologies will require significant investment and collaboration across various scientific disciplines. Moreover, the ethical and societal implications of harnessing zero-point energy cannot be ignored. Even if technological breakthroughs are achieved, questions about how this energy source will be used, who will control it, and how it will be distributed will need to be addressed. Ensuring that zero-point energy benefits all of humanity, rather than becoming a tool for exploitation or conflict, will be a monumental task. Despite these challenges, there are reasons to be optimistic. Research efforts are gradually becoming more sophisticated, and interdisciplinary collaborations are emerging. Advances in quantum computing, nanotechnology, and particle physics are continuously providing new insights that could eventually lead to practical zero-point energy devices. Additionally, some researchers are re-examining fundamental theories of physics, proposing alternative approaches to harnessing vacuum energy. Concepts involving negative energy states, spacetime manipulation, and quantum gravity are being explored as potential solutions. The pursuit of zero-point energy may ultimately require us to expand our understanding of the universe itself. Looking ahead, the most promising path forward involves a combination of theoretical research, experimental testing, and technological innovation. Collaborative efforts between governments, private institutions, and independent researchers will be essential to accelerate progress. With continued dedication and creativity, the dream of unlocking zero-point energy may one day become a reality. The journey is far from over, but each step brings us closer to answering one of the greatest scientific mysteries of our time. Whether or not we succeed, the pursuit itself will continue to push the boundaries of human knowledge and imagination. Section 3. Inspiring curiosity and further exploration. The quest to harness zero-point energy is more than just a scientific challenge. It's a profound journey that stretches the limits of human curiosity and creativity. Whether or not practical zero-point energy can ever be achieved, the pursuit itself is pushing the boundaries of our understanding of the universe. And that, perhaps, is the most important part of this entire endeavor. Exploring zero-point energy has already led to groundbreaking discoveries in fields such as quantum field theory, quantum optics, and materials science. Researchers striving to unlock the mysteries of vacuum energy are not only developing new technologies, but also deepening our comprehension of the fundamental nature of reality. Every experiment, every failed attempt, and every revised theory contributes to a greater understanding of the universe and our place within it. The possibility of harnessing the quantum vacuum has inspired a wide array of interdisciplinary research efforts. Physicists, engineers, mathematicians, and material scientists are collaborating like never before, united by the hope of uncovering something truly extraordinary. Even if zero-point energy proves to be inaccessible, the journey will have produced valuable insights and technological advances along the way. Moreover, the pursuit of zero-point energy encourages us to remain open-minded. Scientific progress often requires breaking away from conventional thinking and daring to explore the unknown. The history of science is filled with revolutionary discoveries that were initially dismissed as impossible. Zero-point energy could very well be the next chapter in that ongoing story. Inspiring curiosity and exploration is essential. As new generations of scientists and researchers take up the challenge, they bring fresh perspectives and innovative ideas to the table. Educational programs that encourage creative problem-solving and interdisciplinary collaboration will be crucial for advancing this field. If we are to unlock the secrets of vacuum energy, we must foster an environment where bold ideas can be pursued and tested without fear of ridicule or dismissal. Beyond the scientific community, the broader public also has a role to play. Understanding the implications of zero-point energy and engaging in thoughtful discussions about its potential impact on society are essential steps toward ensuring responsible development. Public interest and support can drive funding, inspire young researchers, and even help guide ethical considerations. Ultimately, the search for zero-point energy is about more than just technology or scientific achievement. It's about our ongoing quest to understand the universe, and our desire to turn the impossible into reality. Whether or not we ever succeed in harnessing this mysterious power source, the effort itself will leave a lasting legacy of knowledge, inspiration, and discovery. And who knows? The answers we seek may be closer than we think. If you found this video helpful or interesting, please give it a thumbs up and subscribe to the channel.